Symmetric ciphers. Symmetric. What is symmetric encryption? The same key is used to encrypt that is used to decrypt. And we use these on stream ciphers quite a bit. So some examples are AES. Okay, so by the way, all the ones in orange are in the pool of questions that commonly come up. They're probably all in the pool, but the ones in orange are the ones that commonly come up. So smart play is to know the whole thing, be familiar with these, but definitely know the ones that are highlighted. So AES, Blowfish, DES, Triple DES, which is just DES, 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 the same algorithm applied 3 times in a row. Serpent, Twofish, Camellia, Cast 128, Idea, RC2, RC5, Seed, Aria, Skipjack, T, and XT. And if you're just listening, that's TEA. So these are symmetric ciphers. Asymmetric ciphers. When I encrypt, I use my key. When you decrypt, you use your key and my public key. So this is the difference. Symmetric uses the same key to encrypt as it does to decrypt. Asymmetric uses the sender's private key to encrypt while adding the receiver's public key. And on the other end, the receiver uses his private key and my public key to decrypt. So actually, it just uses your private key to decrypt because I've already included your public key. You don't need my public key. Asymmetric, by the way, for asymmetric encryption, if I include my digital signature in the email, they can obtain my public key from my digital signature. I don't have to send them a separate key. So it's a little caveat for you. So asymmetric ciphers, Diffie-Hellman, DSA, which stands for Digital Signature Algorithm, ECDH, ECDSA, EDDSA, and EKE, features. Used in public key cryptography, used to build PKI, which is public key infrastructure, and then based on elliptic curve cryptography. So these are pretty hardened algorithms, and that's why they call them PGP, pretty good privacy, and the GNU Privacy Guard uses it also. So Diffie-Hellman, some of the ways you can use this with the bytes and things. So there's this one question that comes up often. Diffie-Hellman group 5 uses how many bits of encryption? 1536. I've also seen it 1536-bit group encryption. Which group does it belong to? Group 5. So you need to know this. I would know this whole slide. It's not that complicated if you look at it. So the first one is 768, 1024, 1536 is the odd one, right? So it kind of sticks out. So the groups are 1, 2, 5, 14, 15, 19, and 20. And then the encryptions, the respective bit groups that go with them are 768, 1024, 1536, and 2048. 3072, those are all in order. And now they come out of order, it looks like. But look, these are the elliptic group or curve groups. So if you think of it about the evolution of encryption, the bits get bigger as they go up from 1, 2, 5, 14, 15, and 19, and 20. But don't let them screw you up. Remember those numbers. What if they said 12 and asked you a true or false? And then you said, well, yeah, that's an order. Timber told me that's an order. Oh, man, I missed that one. Timber lied to me. No, because I'm showing you right here. 1, 2, 5, 14, 15, 19, and 20 are the groups. So make sure you remember those numbers. And you don't have to remember the bits. Just look at the order in which they come in. 768, 1024, 1536, 2048, 3072. And then when you hit the other ones, they look like they're out of order because they're smaller. So don't let that throw you. The elliptic curve group. In evolution, elliptic comes later, and it's very, very, very good encryption. So the elliptic curve encryption comes way later, and there's 256 and 384. So don't let this one mess you up. It looks very hard. Oh my gosh, how am I going to remember this? It's not that difficult. So just look at it, make it make sense to you, spend 15 minutes reading about it, and you'll probably be pretty comfortable with it. What I'm saying will kind of sink in when you sit down and look at this.